call linear programming. And linear programming allows us to do problems that have cost analysis to it. It's actually one of the more practical things to be learned in algebra 2, believe it or not, because you can use it with a lot of different word problems and whatnot. So what we do with this section called linear programming is we use what are called constraints. Constraints are what you're bounded by. So in this case, you're going to be bounded by specific inequalities. Sometimes you'll have 3 of them, 4 of them, 5 of them. I don't believe we get too many of them with absolute value. I'm going to try and stay away from that because it's easier to do it just with inequalities. I mean, the reason they use the absolute value ones, it's you can write one equation as opposed to 2. That's really the only advantage there. But a lot of times here, you're going to start to see quadrant-style problems. For example, I know we talked about this yesterday. When you see x is greater than or equal to 0, y is greater than or equal to 0, what quadrant is this putting you into? 1. Very good. So when I go to make my own graph, all I'm going to do to start with is that. Because that takes care of 2 of my constraints. When x is greater than 0 and y is greater than or equal to 0, it means I'm in the first quadrant, including the axes. Okay? Right off the bat. Yes, ma'am?
When it's saying x is greater than, that means like up, right? No, y is up.
Correct.
And then x is, okay.
Yeah. So one of the things that I'll do is I'll throw an arrow like that. Because I don't want to overshade. Bless you. I don't want to overshade everything. I'm going to use arrows to help make it cleaner.
That's the opposite of what you're saying, right? No.
What do you?
Isn't the y like up or down? No.
But remember, when you're looking at it in terms of when this is your
line.
x-axis, these are your positive x numbers go this way,
So, okay.
and then your positive y values go this way.
So when it says that x is greater than 0, it's going to be either quadrant 1 or quadrant 4?
Correct. And I'm really glad you brought that up because as we go through quadrants, one of the big topics we talk about next semester, excuse me, is the unit circle. And within the unit circle, we still deal with the idea of positive and negative values. We know that everything's positive in the first quadrant. X is negative, y is positive, they're both negative, and then positive and negative. Just like she was saying about in the fourth quadrant, your x values are still positive. Now, what happens as we get into this unit circle is that we build it off of your 2 special right triangles, 30/60s, 45s, and you get values. These unit circle values, as they bounce from this spot to this spot, the y value doesn't change, the x value is symmetrical. So the x value goes from positive to negative. As it moves to here, the x value doesn't change, but the y value becomes symmetrical and changes sign. And it bounces back and forth. So as we get into trigonometry, all you need to know is your 30/60/90s and your 45/45/90 triangle and what quadrant something is positive or negative in. And that will take you through basically we're in trigonometry, this unit circle style stuff. That will take you through the better part of 6 to 8 weeks of what we learn about it. And then when you do that again the following year, even more so on crack in pre-calc, you'll be like, oh, that's right, Murphy was right, because it's all built out of 1, 2, 3, 4. That's it. So it's important to remember where your quadrants lie. Anyway, back to this one. Now, am I going to go to slope-intercept form, or am I just going to do a quick graph? Quick graph, absolutely, because otherwise it's just a pain in the butt. So, first one, what's your x-intercept? Negative 15. My y-intercept at 5. So,
Wait, how do you do
remember when you're crossing the y-axis, what's your value of x? 0. When you cross the x-axis, what's your value of y? I'm plugging and chugging.
that? Oh, okay.
That's all I'm doing. It's called a quick graph. So I know that I'll be back here at negative 15, comma 0 for my x-intercept, and then at positive 5, at 0, 5 for my y, which means my line will do this. I don't worry about this back half of the line because it's not already within my first two constraints. But I still have to test it. Did I draw that through the origin? No. What's 0 plus 0?
0.
Is it smaller than 15?
Yes.
So I'm shading downward. So right now, I'm pushing this one downward. So now my feasible region has become into this shape. See how I wedged it off from the top there? That's kind of what you start to do.
Why'd you ask if it was smaller than 0? 0.
I'm doing that test one again. I put in 0, 0 for that
Oh.
because it didn't go through it. So I'm going to consistently use that if I can.
Okay.
And now do the same thing with the next one. What is your x-intercept? Your y-intercept. So I put one at 6, at 6, 0, and I put the other one up here at 0 and 12. And I know that I have to go this way. Okay. Now, notice one thing. I intersected this other line here. I don't know what that ordered pair is, but I'm going to figure that out. But I'm going to shade it. Where am I going to test it at? 0, 0. What's 0 plus 0?
0.
Is it smaller than 12?
Yes.
So now I've created
Oh, okay.
this shaded region. I've created a constraint boundary area with 4 ordered pairs. At the origin of 0, 0, at an intercept at 6, 0, at something we're going to figure out, and the other one at 0, 5. Well, when I'm looking at that equation there, all I have to do to find out that other intersection is solve that system of equations, just like we did 2 days ago. So to find that intersection point, we can do a couple of different things here. I could get, I can do linear combinations, I can do whatever. I'm seeing since I have a negative x and a positive 2x, I'll take that top equation and multiply it by 2. And that way I can figure out the actual intersection point of those two lines. So if I do that, I get negative 2x plus 6y is 30. You okay with that? I'm going to add them together so the x's have now been eliminated. Remember, you use linear combination to get to an elimination style problem to get rid of it. So I have 7y is 42. One other quick thing I want you guys to notice. When I'm solving these systems, I don't care that they're inequalities. I'm solving them as equal because I'm looking where they run into each other. Is that okay? That's all I'm doing. What's y? 6. So y is 6. And if y is 6, if I substitute back here, what's x? 3.
Wait, what point is that giving us?
Where it's given us the intersection of where these two lines run into each other. Because a lot of times what's going to happen is that if we had some actual cost function we have to test, which we will here in a second, we would check it at the 4 ordered pairs to see which one gives you a maximum value.
So if you have two equations for two lines that you're graphing,
Yeah.
and you like solve them a system of equations, it'll give you the point that they intersect.
That's the whole point of systems of equations. What value makes it true for both of them? The value that makes them true for both is where they intersect.
Yeah, that makes sense. Okay.
What happens if they're like different signs? Like if it's like negative x plus 3y is less than or equal to 15, what if that is greater than or equal to 15?
When they intersect, we don't worry about the inequality part at all, because we're just looking to see where they run into each other. So you can disregard the idea of the inequalities when you're solving the systems. Okay? They still hit each other, so there is going to be one exact value where they hit, and that's what we're just looking for. Yes, ma'am?
Where did you decide why it was 42?
I added these two equations together by using that linear combination. So I multiplied that top one by 2, rewrote it, and then I just added them together to eliminate.
Okay,
Okay.
and why'd you multiply by the top one by two?
Because I saw I had a negative x, so if I double that, I get negative 2x. That's why 2 times 3 and then 2 times 15, that just gave me all that.
Oh, okay.
Okay? That's the kind of idea of what we're going to be looking at, where we're going to try to find this feasible region, find the ordered pairs that these shapes create. Okay? Let's try another one. I'm going to save some of these things. And we'll add this little maximum value. This C function, where it says find the maximum value of C equals negative x plus 3y, that's going to be called your, it's going to give you something to maximize. It'll give you that equation. Okay? You're trying to figure out what ordered pair creates that. So we have x is greater than 2, x is less than 5, y is greater than 0, and the equation y is less than or equal to 2x plus 12. Of those, we know that it's going to be y is greater than or equal to 0, so we know it's going to be moving up. If I throw an x value here at 0, I know I'm not going to have to worry about it because I'm going to start it at 2. So this is at 2, 0, and it's going to the right. Are we okay with that? I put another one up at 5. And it's going to the left. That's somewhere in there because the y value is moving up.
Yeah.
So we have an open cylinder or an open rectangle. There's no lid on it. The next function allows me to put a lid on it. Yes, ma'am?
Wait, so y is greater than 0, isn't that the y-axis or no?
The y-axis, remember, is here, but as y is greater than 0, isn't it moving up?
Okay.
Because remember how you're counting, because you start at 0, 1, 2, 3, 4, 5, 6, 7, and so on. So as y is moving upward, it's going larger.
Okay, so you, for this, when it says y is greater, you count the line that goes, no,
The other way. Yeah. Y is greater than 0 is always going up.
Because like below it is negative.
But then why does it have to be above the x?
Remember when you have your ordered pair, when you have your x values are here, your y values are here. Here's 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Which way is y greater than 0? Up. Yes. We just draw it from the x line because that's
Yeah,
the
that's what I
bottom.
was talking about, like.
We
why
draw
is
it.
the next
Because that's where 0 is.
one? Oh, okay.
Okay, so as it starts from 0 moving up. Okay. Here it's in slope-intercept form, but you might realize that it's quicker to put it in standard. Here's what I mean. If I rewrite this as 2x plus y less than or equal to 12, isn't that the same thing? Because now I do quick graph. What's your y-intercept? What's your x-intercept? 6. 0, 12.
How can the points be there if y is supposed to be like between there?
What do you mean?
Between 2 and 5?
Mhm.
Like how come the points are outside of it then? If, like,
We haven't gotten there yet. How many points do you need to create a line?
2. So it is between there, but
What's 0 plus 0?
0.
Is it smaller than 12?
Yes.
So this one is shaded inward, which means we've created
but you have to shade it inside that.
Yep.
Yeah. Okay,
We
that
have
makes
created our
sense.
boundary now of these 4 points. And you know your x values here and here because they're vertical from 2, 0, which means this x value is at 2, comma something. This one is at 5, comma something. Well, how do you find that something?
System of equation.
Just substitute in,
Oh.
okay? Since you know that it's on that vertical, you substitute in 2 for x, you substitute in 5 for x. What's 2 times negative 2? What's negative 4 and 12? 8. That ordered pair is at 2 and 8. What's 5 times negative 2?
-10.
What's negative 10 and 12? 2. Bless you. So now you have 4 ordered pairs that you've created from your constraints. That's the boundary of your feasible regions. So you would use, since using our quick graphs, we take our ordered pairs of 2, 0, 5, 0, 5 and 2, and 2 and 8, and we substitute into our maximize function. What's negative 2 plus 3 times 0? What's negative 5 plus 3 times 0? What's negative 5 plus, bless you, 3 times 2? What's negative 2 plus 3 times 8? Which one of those values gives you the maximum function? The maximum. The bottom of the one. We have this, because this one is negative 2, negative 5, 1. What was that, 24, so 22. So your maximum occurs at 2, 8. And it all stems from drawing that little picture. Yes,
It's a
ma'am?
lot easier to like do it all than like be given the shaded figure and actually figure it out.
Yeah, but there is validity in being able to work backwards stuff. There is validity in knowing how to do that.
Yeah.
Okay.
I just think it's easier like doing starting from scratch.
So you have to do all of that in order to find the max value.
Yeah.
Okay.
And believe me, as we do more of these, it gets really easy. It really does. What's wrong?
I was just trying to figure out quick graphs, and then I look up at the board, and there's a bunch of red stuff.
I think we have time to do one more, okay? Graph paper, schmack paper.
Oh my gosh, that's small.
We don't need no stinking graph paper. Let's see, so we have x is greater or equal to 0.
Wait, what's going, Mr. Murphy? Wait, so the greatest, our final solution was that the greatest.
The maximum value occurred at 2.8.
Maximum value occurred at 2.8.
That's
Okay,
all.
I was trying to do something with the number 22. I was like, what's up with the number 22?
It just said that was the biggest value for,
Yeah.
because when we go to use these what are called test points, these corners of these polygons, whatever you wind up creating, will give you maximum values or minimum values. This case was a fully enclosed figure, which meant that there's going to be a maximum and a minimum. Sometimes there's no lid on the top, which means there's no maximum value. Sometimes there's no lid on the bottom, which means there's no minimum value. So these things can occur depending upon the style problem. It'll ask you. Usually it's maximum because you want to make money.
Well, if you find the maximum, don't you like automatically find the minimum? Because like 5.2 was the no. Both of these are the minimum. 2, 0, and 5, 0.
But if you look at it, which one of those was smaller?
2, 0. Wait, it says they're both negative 2.
I thought one of them was negative, one of them was like 1 and the other one was negative 2 or something. 5.
Oh no, one of them was negative 5.
Yeah, so that would be technically your minimum.
I just.
Don't get me wrong, there might be times where you could get both points being the same, but I think it's very rare. So x is greater than or equal to 0, which means I'm first, fourth quadrant. All right, I know I'm going to be first, fourth quadrant
I got that first.
to start with. Y equals 2x plus 2. To be honest with you, I'm going to write it as negative 2x plus y is less than 2, because that way I can do a quick graph.
First and fourth quadrant?
Yeah.
Oh, because it's like that and that. Okay.
I have a y-intercept of 2, an x-intercept of -1.
Joe, just
So we kind of need some of the second one.
Yeah, and that'll happen. And then I connect them through. Is 0 smaller than 2?
And, yes.
So I know this is moving this way. So right now I'm bounding over here. And I do the same thing with the 5. What's your x and y intercept when it's x plus y equals 5? 5. They're both at 5. So one here at 5. And then one here at 0, 5. That's what comes through this way too. What's 0 plus 0?
0.
Is 5 greater than 0?
Yes.
So I'm moving backwards again. So I have one intersection point here that I have to find. Because in this case, since it's x is greater than 0, that's going this way, is there a floor to this problem?
Yes. It's the little.
No.
Oh, that's it.
No, because there's nothing that says y is greater than 0, so there's no floor to this one. So this is a case that there's no minimum value.
But it can't be shaded in the 2 or 3 quadrants, right?
Correct, because of this.
It wants the minimum value, so how do we find the minimum thing? Nothing.
No minimum. That's what you would say.
Oh,
See how the floor here drops out? It's the trapdoor of death.
I like this one better because we have
And now to figure out the other one, all we have to do is just substitute in. Real quick here, since we have y equals 2x plus 2, I'm just going to say 5 is x plus 2x plus 2. I'm just using direct substitution. Are we okay with that?
Sure.
It's just substituted in the 1.
I'm finding the intersection of these two equations. Since I remember, when you're finding the intersection, don't pay any attention to the fact of the inequalities. Man, we're running out of time. I need to show you really fast where to find the homework for tonight. What I did is
Monday night.
I only want you to do a couple of them. So
Yay!
what I did here for today is that the textbook we have right now isn't all that great for these style problems. So I'm going to supplement with the old material. So hence the tab that says Old Algebra 2 book. We click. And it's right here. It just opens up. This tab will open up as a PDF file.
Click here.
All right. And originally I wanted to do 12 through 20. I don't know if we'll have to. That's a lot now that you guys are still working on these things. Let's do 12 through 20, but let's just do the evens, okay? Just to get it started.
What page?
Can I take a picture of it?
It's
166.
yeah, it's up here right now if you want to take a picture of it. So let me see if I can zoom in a little bit for you. Oh, here's the top part, and I'll scroll down for you. Let me know you're ready. Okay. So I'll change, it's on the website already. The tab is already there. I know it opens up as a PDF file. Everybody can view it. It should be all right. I'll change it to say evens right now. Thanks, guys. If you want to get rambunctious, read what we're going to do with this.
Murphy, can I have a bus pass?
Yeah.
Have a good weekend.
You too, thanks.
Mr. Murphy, can I have a bus pass?
Yeah.
I'm just gonna do the homework downstairs.
What's today, the 2nd? I got to go grab more of them. Here you go. See you guys. Wait, did you show your sister the picture at all?
Yeah, she's like, oh no.
Oh, that's awesome.
Mr. Murphy.
What's that? It's on the website. It's under the old book tab. Old book tab. No, my website. Old book tab. It should be right there. It should pop right up. There it is. Yes, sir. What's that? Fine, I think. I haven't had to yell at anybody yet.
good day.
You too.
Have a good weekend.
Ish. You're right. You okay with all that? What's that? Do the 12 through 20 evens on that, on these 2 pages. Yes, sir. I'm gonna change it. You probably saw it here. I already wrote it. I'm just gonna change. I'll change it to say evens. I'll do that right now. All right. Do 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 do. All right, I just changed it to say even, so it should. By next time you open it up, it should say that. Isn't technology great when it works, right? All right, have a great weekend.